In this video, we're going to develop the formula to find the arc length or length of a curve over some interval. And in the next video, we'll talk about that surfaces of revolution, but it really does require the use of this first formula that we'll talk about here. Say I've got some function, f of x, that I want to try to find the length of between two x values. So between a and b here, I want to know what the length here is, okay? And there's kind of a nifty way to do that. We have to look a little bit closer. So let's zoom in just a pinch. I'm going to say this length here, it would be really nice to be able to just kind of cut it, like, you would cut a string and lay that string out and measure it, with a ruler. And we're kind of going to think about it that way, but more so along the lines of zooming in and taking tiny, tiny pieces of that string and adding those tiny pieces up. This is going to be an integration process. But let's develop where those kind of parts come from. And the way I'm going to do it isn't exactly the rigorous way. I'm kind of going to jump over a few difficult spots, but I think the core concept will still be there. So what we want to do here is say I want to kind of focus in on two x values, x and x plus delta x, or some small little change in x, and I want to zoom in there. And if I resketch what my curve might look like, if I zoom in really, really, really far, what I've got is really kind of this pretty, straight piece of curve that I can kind of estimate or get really close to figuring out what the length is, okay? And I'm going to put those points back there on my curve. They would be like x, f of x, and x plus delta x, f of x plus delta x. And I'm going to call that distance that I want then. I want just kind of a little piece of it. I'm going to call that ds. All right, so kind of between those two function values, I'm going to try to find the length of my curve there, ds. And what we're going to do is we're going to take advantage of some right triangle trig here. We're going to take advantage really just of the distance formula. So if I kind of try to sketch in here a horizontal and a vertical, connecting those 2 points, I can describe those distances as like some change in x and some change in y. And we're going to kind of, like I said, this is one of the difficult parts we're going to kind of jump over. I want to describe them as like a dx and a dy. There's a little bit more going on behind the scenes, but basically I'm able to say that these two distances can take the form of like a dx and a dy. All right, I'm going to copy this picture again here on the next slide. And what I see then is to find that distance ds, I have the ability to use the distance formula, which comes right from my Pythagorean theorem. Okay, so distance ds is actually the square root of the side lengths squared and added together, right? And I'm going to manipulate this so that I can work to find what I would call s. And I'm going to do that through some integration, but first we need to kind of shape this radical, this distance, a little bit nicer. So what we do here is we factor out a dx. And when I do that, there's a 1 plus dy squared over dx squared. And you're going to see very quickly why I decide to do that. I'm going to play a little game where I kind of make some changes here. I'm going to take this guy, my dy squared over dx squared, and I'm going to pull out my squared, right? I'm squaring both the numerator and denominator. I can pull out that squared. And that's going to look a lot like our derivative, dy dx, right? The derivative of y with respect to x. And that's going to be, given my function, f of x, f prime of x. I'm also going to take a dx squared and pull that out of the radical. But when I do that, I have to take the square root, right? So when that comes out, it turns into just a dx instead of a dx squared. What's left inside the radical should be a 1 plus, and again, that should be like an f prime of x, quantity squared. So given the function that I had on the previous slide, I'm able to take a derivative, square it, add 1, take the square root, multiply by that dx distance there, and that should give me the length of this tiny little hypotenuse, okay, ds. Like before, we were taking things in pieces parts and adding them up over the entire region that we were working with, whether it was with areas or volumes. We were taking slices, little tiny snapshots, and adding them all together through integration. That doesn't change here. I'm going to say that S, the actual length of the curve from A to B, is going to be the integral from A to B of my ds there. Okay? So I'm just going to substitute ds in 1 plus f prime of x quantity squared dx. That right there is the arc length. The arc length of f of x on the interval from A to B, okay? So this formula is, of course, specific. If I've got a function defined as a function of x, and I'm coming across some x interval, okay? The formula changes just a little bit if I have to do something with respect to y, but the idea is exactly the same. Like I said, I've skipped over a few kind of rigorous bits here. If you want to see those, they're available in the textbook and, of course, through other online resources. I'm going to do an example or two here where I actually use and apply this formula, and they're going to be pretty straightforward. I can't leave really too much information out for us to be able to find an arc length. So, for example, let's find the arc length of y equals 2/3 x to the 3/2 on the interval from 0 to 3. Okay, so that function has a fractional exponent there. I don't have a graph of it. You could, of course, plot one, use some software to find a graph of that function. I don't really need it. Really, all that I need is my function here and the bounds. So what I'm able to do is just look at that function there, and I know really all I need is f prime of x, or dy dx, and I take just a quick derivative with my power rule and end up with x to the power 1/2. So the derivative of that function is x to the 1/2. Okay, that's going to show up in my integral under the radical, and I've got to square it. So let me write that formula out again. S is equal to the integral from 0 to 3 of 1 plus x to the 1/2 quantity squared dx. Okay, that's it. If you want to go back a little bit, you can see that formula in its entirety. But the only thing I've changed are what I've put in color there, in light blue and in pink. Those are the only two components of this we actually need. So it's a little bit less involved than working with areas and volumes. Mostly things are going to be straightforward here. Some of the difficulty might come with integrating because I've got this square root, and that can be difficult to work with. But thankfully, this specific example boils down rather nicely, as x to the 1/2 squared leaves me with 1 plus x under the radical, right? And that's something that I can integrate right away. If you want to do a substitution with u, you can. U would be 1 plus x. Du would then just be dx. There's not any consequence for making that substitution in terms of the derivative. So when I integrate, I'm really just kind of using my power rule here. Adding 1 to the power, I should have 1 plus x to the 3/2 divided by the new power. It's that 2/3 out front, multiply by 2/3, and then evaluate from 0 to 3. Okay? Plug in 0 and 3, and I see that there being a 2/3 out in front, I'm going to keep that out in front. I end up with a 4 to the 3/2 minus 1 to the 3/2. And those numbers break down rather nicely. 4 to the 3/2 ends up as an 8, and 1 to the 3/2 ends up as 1. 8 minus 1 is 7, times 2/3 is going to give me a 14/3. So that length, the length of my curve on the interval from 0 to 3, is 14/3 units long, right? If I were to take it, cut it, pull it taut and straighten it out and measure it, it would measure 14/3, right? So just what? A little bit more than 4 units, a little bit less than 5 units. Okay. Another example here. pretty much the same question type. Find the length of y equals natural log of cosine of x on the interval from 0 to pi over 4. So this is a function that's pretty doctored to work in a nice way with arc length here, and we'll kind of show you why that is. Also trying to reincorporate some of the things we talked about in our integration review. So what I do is pretty much handle this the same way. I need a derivative of my function, dy dx. Derivative of natural log of something is 1 over the something with chain rule, so 1 over cosine times the derivative of cosine is minus sine, and those can multiply together to give me minus tangent, okay, minus tangent of x. I need to square that and put it under the radical in my arc length formula. So I see that s is equal to the integral from 0 to pi over 4, the square root of 1 plus tangent squared, right? When I square negative tangent, I end up with tangent squared. And then I have to integrate this somehow. I remember 1 plus tangent squared shows up in one of those Pythagorean identities, and in fact 1 plus tangent squared is going to be secant squared. So I can replace 1 plus tangent squared with secant squared of x, take the square root to give me just secant in my integral, and then actually find that antiderivative. This antiderivative you would have seen probably last semester calculus. It requires a little bit of multiplication and then a u substitution, but you're able to integrate and end up with something like the integral of du over u. This is a natural log, and the inside we end up with secant of x plus tangent of x. Okay? Same as before, fundamental theorem of calculus, evaluate at pi over 4, and what I end up with, secant of pi over 4, is 1 over cosine of pi over 4. Cosine of pi over 4, we remember, is radical 2 over 2. And I want 1 over that, so the fraction is going to flip. I end up with 2 over radical 2 plus 1 when I plug in 0 for tangent. Tangent of 0 tangent of pi over 4 should be 1, minus what I get when I plug in 0. Secant of 0 is 1 because 1 over cosine of 0 is 1 over 1, plus tangent of 0, I get a 0. Okay? 1 plus 0 in that second natural log is going to give me a 1, and natural log of 1 I know to be 0. 2 over radical 2 is actually rationalized as radical 2, and all I have left then is natural log of radical 2 plus 1. I could drop the absolute value signs because radical 2 plus 1 is indeed positive. There isn't really anything to worry about with those absolute values. That's just a quick kind of derivation and some examples of the arc length formula. Nothing too involved, pretty straightforward. The only change might be is if I have a function described as a function of y. Okay? But other than that, that's what I want you to know. Thanks for watching.